Alrighty, so we're going to talk about pendulums today. So pendulums are very similar to springs, but instead of spring potential energy, we're going to be dealing with gravitational potential energy. So for a lot of students, thinking about pendulums is much easier. I'm also going to think about pendulums in terms of when you're swinging on a swing set. So think about yourself as sitting on a swing set. What it feels like, where you're going the fastest, where you're feeling like you're getting pushed into the seat of the swing the most, those kinds of things when you're thinking about a pendulum. And I've found that that really helps students to better understand and visualize what's happening. So the first thing that we need to do when we're talking about uh, pendulums is just identify what energy is where. And so maximum gravitational potential energy is going to be at points 1 and 3. So points 1 and 3 because they're at the highest point. So the higher up you are, the more gravitational potential energy you have. And then the second question is, where is the maximum kinetic energy? Well, kinetic energy is going to be going the fastest. And if you think about swinging on a swing, you're going to be going the fastest at the bottom when you're close to the ground. And so that's at point 2. Where is maximum acceleration going to be? We will talk about this more in a little bit, but your maximum acceleration is going to be at points 1 and 3 because of the direction of the forces, and that's where it's going to be causing you to speed up and slow down the most. So as you reach point 1, you're going to be slowing down, and then as you move away from point 1, you will be speeding up again. And so that's where you're going to experience the biggest acceleration. And then where's the maximum force? So this is where it's the easiest when you think about swinging on a swing set. If you swing really, really high, I know that I feel like I'm basically weightless up at the top. Whereas at the bottom, you can really feel yourself getting pushed kind of down into the seat of the swing a lot more. And so that's where you're going to have your maximum force. So that's something that you can just memorize, but that is also something that we're going to calculate today. Is we're going to calculate the force in the pendulum, in the string of the pendulum at point 2. So I'm going to give you like the conceptual what we're doing steps in the presentation, and then on my iPad I'm going to be showing you guys an actual example and applying it. You will have links to both of these things in the Google Classroom. So go ahead and take a look for those. So what is the maximum tension in the string during the oscillation? Well, we just talked about that. That is at point 2. But if we're going to actually calculate it, we're going to need to know not only where the tension is the greatest, but we need to know how fast it's going. How do you determine the acceleration to go in a circle? And how to draw the force diagram and solve for the tension in the string. So this is kind of like a 4-step problem. So if I ask you to solve for the tension in this string, you really have 4 things that you need to do. So the first thing is that the tension is the biggest at the bottom. The second thing is that we need to figure out the velocity at the bottom. So we're going to need to use the angle to find the change in height of the pendulum. And the way that we're going to do this is we're going to remember that the pendulum itself has some length of L. So here, when it's straight up and down, that's how long the pendulum is. When it's up here, the length of the pendulum is still the same. The string has not gotten any longer. So I've drawn those both as blue. And then the second thing that we're going to do is we're going to use the angle here to find y, which is the height from that pivot point to however high this is now. And so that height y is what we need to figure out. So we'll use some trigonometry to find the height y because we're going to have the hypotenuse and we're going to have the angle, and then we'll just solve for y. And then to get this difference in height, which is what we're trying to find, I know the whole length is L. So that way I can just say, well, if I take the whole length and I subtract how long y is, then I know how much h is. Once we have that height, we're going to use conservation of energy. And the way that we're going to use conservation of energy is up here at the highest point, it's going to have all gravitational potential energy. And down here at the bottom, it's going to have all kinetic energy. So because we know that, we will be able to calculate gravitational potential energy when we have the height, and then we'll be able to solve for my velocity at the bottom. But why do I care about velocity? Well, I care about velocity because this thing is going in a circle. Okay, so if it was going fast enough, it would go all the way around in a circle. And so right here at the bottom, the ball, although it's not speeding up or slowing down, the direction of the ball is changing, which means that it is accelerating towards the center of the circle. It's nice because the only acceleration we have to deal with at the bottom is only the acceleration due to it going in a circle. I don't have to worry about it also speeding up and slowing down. Therefore, the acceleration to go in a circle, so really this is at point A, but that C represents the acceleration to go in a circle, is v squared over r. So that's why I need my velocity, is because I need to calculate the acceleration to go in a circle. And then once I have that acceleration, then I can do my net force equations. So I'm going to draw my force diagram here. So my force diagram, I have my tension going up, my gravitational force going down, and I know my tension needs to be bigger because I'm accelerating in a circle. And because that acceleration is v squared over r, when I write my net force equation, the stuff that goes up minus the stuff that goes down is equal to ma. That's my acceleration. So I just plug in what I know. So tension, I don't know. Fg is just m times g. My mass times acceleration is mass times the v squared over r. Once I've done that, all I need to do is plug in the numbers. So I have my velocity that I just solved for. The radius is going to be the length of the pendulum, and then mass is whatever the mass that's given to me. And I will not be able to cancel out mass in this case because there's no m in front of this ft. So just be really careful you don't cancel out m at this point in time. I know a lot of times in physics we are able to cancel out mass, and this is not one of them because you have to have the m in all of the terms. All right, so now what I'm going to do is I'm going to go ahead and do the example. So I'm going to have an example where I have a pendulum, and I'm just going to make up some numbers here. So I'm going to have my mass of my pendulum is 12 kilograms. The length of my string is 4 meters, and the angle that I'm using is 20 degrees. And so just like in the other presentation, I have the lengths here. These are going to be the same. And so the only thing I need to do then is I need to figure out what that change in height is. So if I look at this, and I'm going to label this y, I know my hypotenuse. I'm trying to find the adjacent, and I have the 20 degrees. So adjacent and hypotenuse is cosine. So cosine of 20 degrees is equal to adjacent, which is y, over hypotenuse, which is 4 meters. I'm going to multiply both sides times 4. And I'm going to get 4 times cosine of 20 degrees. And then I just need to plug that into my calculator. Alrighty. So I get 3.75877 is equal to my y, which is great. Now all I need to do is I need to find this change in height to get from there to the bottom. Well, that's just going to be this distance here, and I'm going to call that h. Well, if I know the whole length of the entire thing is 4, this whole thing here is 4, if I do 4 minus this y distance here, then that'll be minus 3.75877, and I'll be able to solve for my height. And I get 0.2412. So that's going to be this change in height. And now that I have my change in height, I can use conservation of energy to figure out how fast it's going at the bottom. So in a pendulum, I'm going to think about my energy bar chart for a moment. And I'm going to call this the top, even though like it's not the top, it's just the higher part. And then this is going to be the bottom. So at the bottom, I'm going to have all kinetic energy because that's where it's moving. And my gravitational potential energy will be 0 because it's at a height of 0. So I'm making this my height of 0. And then at the top, my kinetic energy is going to be 0. And my gravitational potential energy will be at its maximum because that's at its highest point. And because of conservation of energy and that there's no work being done on our system, I know that these are going to be equal to each other. So the kinetic energy plus 0 at the top or at the bottom is going to be equal to 0 plus my gravitational potential energy at the top. And so then I just need to remember these equations or look them up on my equation sheet. So 1/2 mv squared plus 0, I'm going to just leave that out. And then 0, I'm going to leave that out, plus the mg. And on your equation sheet, this is delta y. In this case, though, what I've used is h. So I'm going to go ahead and put an h here so that we don't get confused, because it's going to be how much the height of this changed. All right, so I'm going to go ahead and move this up. All right, so at this point, I can notice one thing. I can notice that on both sides of the equation, I have one term each, and both of them have an m, so m will cancel out. So those cancel out, and I'm left with 1/2 v squared is equal to g times h. And we're just going to say that g is 10, and h is what we just got up here. That was 0.2412. And on the left side, we're solving for velocity, so we'll leave this alone. Okay. So I have 1/2 v squared is equal to 2.412. I'm going to multiply both sides times 2 to get that 1/2 moved to the other side. And I get v squared is equal to 4.824. And then I'm going to square root that to find my velocity. So square root both sides. And I get a velocity of 2.196 meters per second. All right, so this is the velocity at the bottom. So that's my biggest velocity, which is great because that's where I'm trying to determine my tension in the string. So I need to know the velocity at the bottom so I can find the tension at the bottom. So why does the velocity matter? Well, it matters because as an object swings, as a pendulum swings, it's going to follow a circular path because the radius or length of the string is not changing. And so at the bottom point here, although it's not speeding up or slowing down because there's nothing pushing on it left to right, it is changing direction because this string is pulling up on it. And so if you remember, an object going in a circle experiences the acceleration to go in a circle, which is v squared over r. So we are going to need to do a force diagram in order to determine our tension in the string. So at the bottom, the only forces acting on this are our gravitational force and the tension from the string. And that tension is bigger than our gravitational force because it's accelerating upwards because that's where the center of the circle is. All right, so then my net force equation, I do the sum of the forces in the y direction is equal to my tension minus my gravitational force, and that's equal to mass times acceleration. In this case, it is the acceleration to go in a circle, so I will be using this and putting it into my acceleration. I don't know Ft, so I'm just going to leave that as Ft, minus gravitational force is just mass times g. And over here, I'm going to use mass times the acceleration to go in a circle, which is just v squared over r. So at this point, the only things that we need to do is we need to start plugging in what everything is. So let's remember our mass was 12 kilograms. So I can put in 12 kilograms for my mass. G is just 10. Mass is still 12. I don't know my Ft, so I'm going to just leave that alone. And then I need my velocity and my radius. So my radius was 4 meters because that's how long the string is. So divided by 4 meters. And then the velocity I got up here was 2.196 meters per second. And that velocity gets squared. All right, so then I just need to solve this. So on the left-hand side, I will have Ft minus 120. On the right-hand side, I'm going to go ahead and type this in the calculator. And I get 14.472. So then all I need to do is add this 120 to both sides. And I get a tension of 134.472. And it's a tension, which means it is a force, so I will have units of newtons. And that's my answer. So this is the tension at the bottom of the pendulum swing. So now that we've found the tension at the bottom of the swing, what I would like to do is go ahead and look at what we need to do to find the tension at the highest point when the pendulum is at rest. Alrighty, so now we want to find the force or tension in the string when it's at its highest point. So if you have your gravitational force going down and the tension, it will be in the same direction as the string, then we will be able to calculate that tension. Now, as a side note, I want to also think about our acceleration and our velocity at this point. So at this moment in time, our velocity is 0. And a little bit ago, we talked about how the acceleration to go in a circle is v squared over r. Well, that means that at this moment, the acceleration, because it's going in a circle, is going to be 0 because the velocity is 0. So that means the acceleration to go in a circle is going to be 0. But that does not mean that the acceleration is 0. In fact, we are going to have a net force because gravitational force is pulling it down and to the left. It is going to accelerate. And specifically, it has to accelerate tangent to our circle or parallel to the side of the circle, or you could think of it as perpendicular to the tension force, because that's the only way that this ball can move because it's attached as a pendulum. So that means that we need to be able to find the acceleration that is tangent to that circle. So what we're going to do is we're going to go ahead and redraw this, or I'm going to just rotate this, which is what I recommend you guys do, is just take your drawing and rotate it such that your tension is up. Okay. And by doing that, now I can look at my forces. It's going to be accelerating to the left because that is what was perpendicular to my circle. So I can redraw this here. Oops. Okay, so to know how much acceleration we have parallel to the edge of this circle or tangent to this circle, I need to know what's going on in this direction. And so when I talk about my net force equations, I'm going to make this my x direction, and I'm going to make this my y direction. So then in my y direction, I'm going to have my tension minus my gravitational force. And in that y direction, it is not accelerating because my velocity is 0. So if I think about this part again, that is the direction that it would be accelerating if it was moving. But I am not going to have that because it's not moving. So this is just going to be MA, where my acceleration is 0. And then for my sum of my forces in, and this is going to be FGY. I need to be careful there. Because not all of gravitational force is going this direction. But I'm going to say FGY, that's going to be how much is going in that direction. And then I will also have an FGX going in the X direction. So as part of this problem, I want to figure out two things. One, I want to figure out the tension in the string when this pendulum is at this maximum height. And I also want to know my acceleration when it is up this high. So the first thing I want to do, just because I'm already here in terms of my sum of my forces in the y direction, is I want to find that Ft. And so I'm going to think about my original diagram again. And I'm going to see that this angle here is 20 degrees, and this was straight down, and FG is also straight down. So that means this is also going to be 20 degrees here. And if that's 20 degrees, then when I look at my rotated version, this is also going to be 20 degrees. So when I go to find FGY, FG is my hypotenuse, that's the pink one. Well, FG is just mg. So I know the hypotenuse, and I need to find the adjacent. So that means I'm going to do cosine. So let's just do like a little side comment here. Cosine of 20 degrees is equal to adjacent, which is FGY, over hypotenuse, which is mg. And then I'm going to multiply mg to both sides, and I'll end up with mg cosine of 20 is equal to FGY. And then I just need to plug in my numbers. Well, my mass is 12, g is 10, and cosine of 20. And I'm going to go ahead and put that into a calculator. All right, and I will get 112.763 for my FGY. So now that I have that FGY, I'm going to plug it in up here. So FT minus my FGY, which is 112.763. And that'll be equal to mass times an acceleration of 0, which will be 0. Add 112.763 to both sides, and I'll get a tension that's equal to 112.763. Thinking about sig figs here, I did not give you very many sig figs, so I would not include all of the decimal places. I would just put Ft is equal to 113 newtons, and that would be your answer for the tension in that string. Now, unfortunately, that is not going to help us find our acceleration because our acceleration is perpendicular to that. So what I'm going to need to do for that is I'm going to need to do the sum of my forces in the x direction. Well, in the x direction, the only force I have is Fgx. And that'll be equal to mass times acceleration. And so I'm going to have to do trig again, but now I need to find it for Fgx. So in this case, I will be using sine of 20 degrees, and that'll be equal to my Fgx, because that's my opposite, over hypotenuse, which is mg. And I'll end up with mg sine of 20 degrees. Mass is 12, g is 10, and then times sine of 20. And let me type that into a calculator. Alrighty, so now I have 41.04 is equal to my FGX. And so I can plug that into my net force equation. So I'll have 41.04 is equal to my mass, and my mass is 12 kilograms. My acceleration is what I'm solving for. So I'm going to go ahead and divide both sides by 12. The 12s will cancel out. And I'll end up with 3.42 is my acceleration. And so that'll be 3.42 meters per second squared. And so this is going to be the acceleration at the top. Alrighty, and the last thing I'd like to do is go ahead and compare the acceleration and force at the lowest points and at the highest points. So the force at the highest point, when the pendulum is swung up the highest, we calculated as being 113 newtons. And to compare that, the force at the bottom of the pendulum swing at the lowest point is going to be 134.472. So that's good because we said that the force at the bottom was going to be bigger than the force at the top. And then the other thing that we can check is the acceleration. So the acceleration at the bottom of the pendulum swing, I went ahead and plugged in the numbers and solved and got 1.206 meters per second squared for the acceleration at the bottom of the pendulum swing. We said the acceleration at the top was bigger, and we definitely got that. So our acceleration was 3.42 meters per second squared at the highest points of that pendulum swing. So we're good. If you have any questions, please let me know.